So when you're in the water, your body feels lighter. Okay. And that's because there's a buoyant force acting on your body. All right. So you're in the water and let's see. Let's get somebody going here. So here you are. Doo, 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 doo. All right, and you're swimming. Okay. So part of your body is displacing water like this. And that results in what we call the buoyant force acting on your body. And that buoyant force depends on how much volume is being pushed out of the way. Okay. And so it's kind of like a reverse weight. Normally we think of the weight as an mg. But what we want to do with buoyant force, it's really the mass of the water that's been moved. So we usually think of it as the density of the water times the volume of the water and then times g. And you'll notice that rho times volume is a mass, just like that, okay? All right, now, so what we're going to do, we're going to look at this situation where we've got a treasure chest underneath the water, and it's got a particular mass here, and it's got a particular volume, but I don't want to use that volume. I want to use this volume, 0.06, just like that, okay? And actually, let's not even do that. Let's go back. Let me go back here. Okay. Let's actually make some estimates here. Let's say our treasure chest is let's say it has a length of 0.5 and it has a width of 0.4. These are meters, 0.4 meters. And it has maybe a height of 0.3. Okay. So that makes it, about yay wide and long and yay wide and yay high, which seems to me to be pretty reasonable for a treasure chest. I remember, I was on a pirate ship for several decades in the 17th century, and that seems about right to me. So, but that was another lifetime ago. Obviously, I'm kidding. I don't believe in reincarnation. Okay, but anyway, I wanted us to see if you go 0.5 times 0.4 times 0.3, that's actually a small number. That's where I got the 0.06 number at. Okay, so our object that's this by this by this, that's only 6% of a cubic meter. Okay, so the thing is, a cubic meter is pretty big. All right, it's pretty big. So in my first set, when I was going through this and I used the number that's there, 0.65, I was like, oh, that seems fine. Started doing my calculations and it was like things went a little bit crazy. So I was like, so I needed to redo that volume on that. So there we go. Now, let's think about the forces that are acting here on our chest. Okay, and so we're obviously going to have the weight. Okay, and then there's going to be the buoyant force. This is the weight. And then there's also a normal force from the sand that's pushing up on this thing. Okay, now if we transfer those to our free body diagram so we can kind of get an idea what's happening, we're going to see that we've got the weight down. Here's my normal force, but here's my buoyant force as well. So the buoyant force actually helps out my normal force. Okay, and so the normal force isn't going to hold the entire weight. Okay, and this is what you feel when you're in the water. Okay, you can kind of maybe bounce on the pool floor or the lake or wherever you are. You feel your body feels lighter like that. Okay, and that's because of the buoyant force. All right, so what I want to do is to try and figure out what is going to be the value of the normal force. All right, so from my free body diagram, I can see what I'm going to be dealing with is, let's make this a little bit bigger. So I'm going to have my normal force plus the buoyant force. It's going to have to equal to my weight. Okay. And so my normal force then becomes the difference between my weight and the buoyant force. Okay. So our weight is the mass of the chest times G minus the density of the water times the volume of the chest times G. So there's my normal force. Okay. All right. Now, so let's get some numbers in there. Okay. So the mass of the chest is 250 kilograms. And we got 9.81 meters per second squared minus 1,000 kilograms per meter cubed times the volume of the chest, which we settled on 0.06 meters cubed, and then G, which is going to be 9.81 meters per second squared. Okay? So let's think about our units per second. Kilograms, meters per second. That's just going to give me newtons. Okay, I got meters cubed there, meters cubed there. So those cancel. I'm left with meters per second times kilograms, which is newtons. Again, just like that. So when I put all that together and get my number, I end up with 2550. Ooh, that's not right. 2450 newtons minus 589 newtons. Okay, so the first number there, the 2450, that's the weight of my chest. Okay, and the second one is the buoyant force there. Okay, now you could see, all right, the density of the water is not going to change, but if for some reason my volume changed, then I could end up with a different normal force. All right, just like that. And we might actually try to find, and we're going to actually do this next, what kind of volume would it take in order for the normal force to go to zero? Because if the normal force went to zero, then the chest would be what we call neutrally buoyant. Okay, so it would just be like in the water. Okay, neither sinking nor floating. Okay, neither sinking nor floating. But we're going to look at that sort of thing here in just a second. But for now, then I'm going to see my normal force is reduced down to 1860. Okay, so there's my adjusted normal force after we take into account the buoyancy. Okay, now I'm going to do one more video in this series, and we're going to work with this scenario again. But what would it take to lift that chest off of the seafloor? I mean, if you were a diver and you discovered this thing and you're like, wow, how can I get this up and onto my boat so I can take it ashore? All right, 250 kilograms is over 500 pounds. Okay, there's no way you're going to be able to pick that thing up and carry it up while you're swimming. All right, that is just not going to happen. Okay, so we need another way to do that. And that's what we're going to look at in the next video. Okay?